you probably think the universe makes sense. Not perfectly, not completely, but enough that the big picture feels stable, like a map that may have missing details yet still points in the right direction. That belief has been carefully built over nearly a century of modern cosmology, shaped by equations that describe how space expands, how matter clumps together, and how light carries the memory of the beginning across billions of years. For a long time, that map worked almost suspiciously well, predicting observation after observation with a precision that made physicists quietly confident they had captured something fundamentally true about reality. And then something small, almost trivial at first glance, began to refuse agreement. And that is where the story you are now stepping into truly begins. A Nobel Prize-winning physicist, Adam Ries, looked at his own data, the same kind of data he had spent decades refining, and instead of celebrating its consistency, he said something unsettlingly simple. We may have misunderstood the universe, not dramatically, not in a way that tears everything down overnight, but in a quieter, more dangerous way, where the equations still work, the predictions still mostly align. Yet somewhere deep inside the model, something does not quite add up. You might expect a claim like that to come from the fringe, from someone trying to overturn established science. But this came from one of the very people who helped build the current understanding in the first place, which is exactly why it matters. To understand why this is so unsettling, you need to see what is at stake. And it is not just a number or a technical disagreement buried inside astrophysics journals. It is the framework that tells you how old the universe is, how fast it is growing, how galaxies form, and ultimately how everything you see came to exist. For decades, cosmologists relied on what is often called the standard model of cosmology, a structure built on Einstein's gravity, dark matter, and dark energy, capable of describing the universe from a fraction of a second after the Big Bang all the way to the present. It is not an exaggeration to say that this model has been one of the most successful intellectual achievements in human history, because it does not just explain one phenomenon. It explains almost everything we can observe on cosmic scales. And that is exactly what makes the current situation so strange. Because the problem did not emerge from a dramatic failure, but from increasing precision. As our instruments became more powerful and our measurements more refined, instead of converging toward a single, cleaner answer, they began to drift apart in a way that should not happen if the underlying model is complete. Imagine you and someone else measuring the same object with better and better tools, expecting your results to match more closely over time, only to find that the gap between your answers becomes clearer, sharper, and more impossible to ignore. That is the position cosmology now finds itself in. Not because of sloppy work, but because of data that has become too good to dismiss. This is where the James Webb Space Telescope enters the story. Not as a hero that resolves uncertainty, but as something far more interesting. A machine that sees deeper into the universe than any instrument before it, and in doing so, exposes details we were not prepared to confront. Webb was expected by many to tidy up lingering inconsistencies, to sharpen blurred observations, to confirm that any disagreement was simply the result of imperfect measurements. Instead, it has done something far more provocative. It has reinforced the very discrepancies that scientists hoped it would erase, turning what once looked like a technical nuisance into something closer to a genuine crack in our understanding. And here is the part that should make you pause. because this is not a story about failure. It is a story about the moment when a field reaches the edge of what it knows and begins to feel the tension of what it does not. Nothing has collapsed. No theory has been discarded, and yet there is a growing recognition that the picture on the box, the one we have been assembling piece by piece for decades, might not be the full picture after all. You are not watching science break down. You are watching it encounter resistance from reality itself. And that resistance is often the first sign that something deeper is waiting to be discovered. If you want to understand where the tension truly begins, you have to focus on a single number. Deceptively simple, almost innocent in appearance, yet powerful enough to split modern cosmology into competing interpretations of reality. And that number is the Hubble constant. First introduced by Edwin Hubble nearly a century ago, when he discovered that galaxies are not standing still but moving away from us, as if space itself is stretching in every direction at once. The Hubble constant is nothing more than a measure of how fast that expansion is happening right now. In this moment, across the observable universe, and at first glance, it sounds like the kind of quantity that should be straightforward to determine, because you are measuring a single property of a single universe, which implies that no matter how you measure it, you should arrive at the same answer. But that expectation is precisely where things begin to unravel, because cosmologists do not have just one way of measuring this number. They have two fundamentally different approaches, and both are grounded in solid physics, careful observation, and decades of refinement. The first method looks backward in time, reaching all the way to the early universe by studying the cosmic microwave background, the faint afterglow of radiation left over from when the universe was only about 380,000 years old, mapped in extraordinary detail by missions like Planck's satellite. From this ancient signal, scientists extract the initial conditions of the cosmos and feed them into the Standard Model, letting the equations evolve forward across nearly 14 billion years to predict how fast the universe should be expanding today. And when they do this, the answer consistently lands around 67 kilometers per second per megaparsec, a value with remarkably small uncertainty and an internal consistency that reinforces confidence in the model itself. The second method refuses to rely on the distant past and instead measures the present universe directly, building what is known as the cosmic distance ladder, a step-by-step calibration that begins with nearby stars and extends outward to galaxies millions of light years away. At the center of this method are Cepheid variable stars, whose brightness pulses in a predictable way that reveals their true luminosity, allowing astronomers to determine their distance by comparing how bright they appear from Earth, and from there they move outward to type Ia supernovae, stellar explosions that shine with nearly uniform brightness and act as cosmic beacons across vast distances. By combining these distance measurements with the observed speeds at which galaxies are receding, scientists can calculate the expansion rate of the universe as it exists today, and when teams like those led by Adam Rees perform this measurement, they consistently obtain a value around 73 kilometers per second per megaparsec. Now, you might be tempted to dismiss this difference as minor, a rounding error that will eventually disappear as techniques improve. But in a field where precision routinely reaches the level of 1% or better, a gap of 8 to 9% is not a small discrepancy. It is a signal that something fundamental may be off. This is not merely a disagreement about a number. It is a disagreement about the history of the universe itself, because the expansion rate determines how long the universe has been evolving, how quickly structures formed, and how far apart galaxies are today. A higher expansion rate implies a younger universe, a different timeline for star formation, and potentially a different behavior of dark energy, the mysterious force driving cosmic acceleration. What makes this situation even more unsettling is that both methods are internally consistent. Both are supported by independent lines of evidence, and both have been scrutinized repeatedly for errors without revealing any obvious flaw large enough to explain the gap. You are left in a position where two carefully constructed measurements, looking at the same universe through different windows, are telling you two different stories, and neither one is easy to discard. It is as if you asked two precise clocks for the time and found them disagreeing, not by a second or two, but by enough to make you question whether they are measuring the same reality at all. And the longer this disagreement persists, the harder it becomes to believe that it is simply a matter of experimental noise, rather than a sign that the framework connecting these measurements may be incomplete. At this point, you might expect the story to resolve itself in the way scientific problems often do, with a better instrument, a cleaner data set, a more precise measurement that quietly erases the disagreement and restores confidence in the model. And for a while, that is exactly what many physicists believed would happen. Because if there was any tool capable of settling the dispute, it was the James Webb Space Telescope, a machine designed not just to see farther, but to see more clearly, cutting through dust, resolving crowded star fields, and capturing infrared light with a sensitivity that made previous telescopes seem almost primitive by comparison. The expectation was simple and reassuring, that Webb would act like a corrective lens, revealing that the higher value of the Hubble constant came from subtle observational errors, particularly in the way Cepheid variable stars were measured in dense, dusty regions of galaxies where light from neighboring stars could blend together and artificially inflate their brightness, leading to underestimated distances and an overestimated expansion rate. This idea, known as stellar crowding, became the most widely accepted explanation for the discrepancy, because it allowed cosmologists to preserve the standard model without introducing new physics. And it fit neatly with the limitations of earlier observations made by the Hubble Space Telescope, whose instruments, while revolutionary for their time, did not have the same ability to penetrate dust or resolve fine detail in distant galaxies. If Cepheid stars were indeed appearing brighter than they should, then correcting for that effect would push their inferred distances farther out, lowering the calculated Hubble constant and bringing it back into agreement with the value predicted from the early universe, effectively dissolving the tension without rewriting the laws of cosmology. So when Webb turned its mirrors toward the same stars that had been studied for years, there was a quiet confidence in the field that the problem was about to shrink, not grow, that the data would finally converge and the narrative would return to one of coherence rather than contradiction. But that is not what happened. And the reason it did not happen is what makes this moment so important. Webb did exactly what it was designed to do. It looked deeper, with higher resolution, through wavelengths of light that bypassed the interference of dust. And when it measured those same Cepheid variables, it did not find them dimmer in a way that would resolve the discrepancy. It found them almost exactly as they had appeared before. The distances held, the calibration held, the expansion rate remained high, stubbornly anchored near 73. Not drifting downward toward 67 as many had hoped. This was not a vague confirmation or a marginal alignment. It was a precise reinforcement of the earlier measurements, now backed by an instrument far less susceptible to the kinds of systematic errors that had been blamed for the tension in the first place. In early 2024, Results published by the team led by Adam Rees made the implication clear. The discrepancy could no longer be easily dismissed as a measurement artifact, because the very tool designed to expose those artifacts had instead validated them. At that moment, the nature of the problem changed, because it was no longer a question of which data set to trust, but whether the framework used to interpret those data sets was missing something essential. What had been described for years as a tension between measurements began to feel less like a technical disagreement and more like a structural inconsistency, something embedded not in the instruments, but in the assumptions connecting our observations of the early universe to our measurements of the present. It is one thing to suspect an error in your tools. It is another to realize that your tools agree with each other and still refuse to match your expectations. And this is where you should pause, because what you are witnessing is not a failure of precision, but the opposite. It is precision becoming so refined that it exposes the limits of the model it was meant to confirm. The James Webb Space Telescope did not break cosmology. It clarified it to a point where its imperfections could no longer hide. And in doing so, it transformed a lingering anomaly into something much harder to ignore. A signal that the universe may be following rules that our current theories only approximate, not fully capture. Once you reach this point, the word tension starts to feel almost misleading, as if it were describing a minor disagreement that patience and better data will eventually smooth away. But what is unfolding here has moved beyond that into something deeper and far more uncomfortable. Because when independent measurements refuse to converge, even after their known sources of error have been carefully stripped away, the problem is no longer confined to technique. It begins to implicate the structure of the theory itself. This shift in perspective did not happen all at once. It emerged gradually as more data accumulated, as more teams repeated the measurements, and as the same pattern kept appearing with a stubborn consistency that resisted easy explanation. At a conference in California, physicist Adam Rees posed a question that captured this moment perfectly, asking whether the discrepancy in the Hubble constant should finally be considered a serious problem. And the response he received from David Gross was telling. Not a cautious endorsement of concern, but a correction of language itself, suggesting that it should not be called a tension, nor even a problem, but a crisis. That choice of words matters, because in physics, a crisis does not mean that everything has failed. It means that something fundamental is being challenged in a way that cannot be ignored without distorting the truth. What makes this situation particularly striking is that both sides of the disagreement are built on methods that have been refined over decades and cross-checked in multiple ways, leaving very little room for simple mistakes to hide. The cosmic microwave background measurements derived from the early universe remain internally consistent and tightly constrained, while the local distance ladder measurements continue to reproduce a higher expansion rate even when observed with the most advanced instruments available. And yet, despite this apparent standoff, not everyone agrees that the crisis is as severe as it appears, which adds another layer of complexity to the story. Because now the disagreement is not just between numbers, but between interpretations of what those numbers mean. Astronomer Wendy Friedman has spent years developing an alternative approach to measuring cosmic distances, one that relies less heavily on Cepheid variables and instead incorporates other stellar indicators such as red giant stars and JAGB stars, which tend to reside in less crowded regions of galaxies and are therefore less susceptible to contamination from nearby light sources. When her team applied these methods using data from the James Webb Space Telescope, The results did not align perfectly with either side of the existing divide, instead falling somewhere in between, with values clustering around 68 to 70, creating a kind of uneasy middle ground that neither fully resolves the discrepancy nor fully confirms its most extreme implications. This introduces a new and subtle possibility that the tension may not only exist between early universe predictions and present-day measurements, but also within the distance ladder itself, suggesting that the very tools used to map the nearby universe might carry unresolved complexities that cannot be eliminated by simply improving observational precision. In other words, even before comparing different methods, there may be hidden layers of uncertainty embedded in the techniques we trust most, which complicates the narrative and prevents any single explanation from dominating the discussion. And yet, despite these competing interpretations, the broader trend remains difficult to dismiss because as more data is gathered, the discrepancy does not shrink. It persists, holding its shape across different analyses and different observational strategies. This persistence is what transforms discomfort into urgency, because in science, anomalies that fade can be ignored, but anomalies that remain demand attention. The field now finds itself in a position where it must seriously consider possibilities that were once treated as speculative, including the idea that new physics may be required to reconcile these observations, whether in the form of an early burst of dark energy that briefly altered the expansion rate of the universe, or some modification to the behavior of matter and radiation in the first moments after the Big Bang. You are no longer looking at a minor inconsistency waiting to be corrected. You are looking at a situation where two well-supported descriptions of the universe cannot both be entirely complete. And the longer this continues, the more it suggests that the gap between them is not a flaw to be patched, but a clue pointing toward a deeper layer of reality that we have not yet learned how to describe. Just when you might think the story could not become any more unsettling, that the disagreement over a single number was already enough to challenge the foundations of cosmology, the universe offers a second, entirely different kind of surprise, one that does not emerge from equations or inferred parameters, but from something far more direct and difficult to reinterpret: the actual appearance of galaxies in the early universe as seen by the James Webb Space Telescope. Because when Webb began looking deep into cosmic history, peering back to a time only a few 100 million years after the Big Bang, it did not find what the standard model had prepared us to expect, namely small, faint, slowly growing structures that would gradually merge and evolve over billions of years into the large galaxies we see today. But instead it revealed objects that seemed far too massive, far too bright, and far too developed for such an early stage of cosmic time. You have to pause here and really feel the weight of that, because this is not a subtle discrepancy buried in statistical analysis. This is a visual contradiction. Galaxies that appear to have assembled themselves with astonishing speed, some of them rivaling the mass of the Milky Way at a time when the universe was less than 1 billion years old. According to the standard model, galaxy formation is a gradual process, shaped by the slow accumulation of matter within dark matter halos, where gas cools, collapses, and forms stars over extended periods, with efficiency limits imposed by feedback processes such as radiation and stellar winds that prevent most of the available material from turning into stars. Under typical conditions, only a fraction of the gas, often around 10%, ends up contributing to star formation, while the rest is heated, dispersed, or simply never collapses in the first place. And yet the galaxies observed by Webb seem to be operating under entirely different rules, as if nearly all available material had been converted into stars with an efficiency approaching 100%, a scenario that strains the limits of known physics. Studies led by astronomers like Mike Boylan-Colchin showed that some of these early galaxy candidates were pushing right up against the theoretical maximum allowed by the standard cosmological framework, leaving very little room for error or alternative interpretation. If these observations were taken at face value, they would imply that either our understanding of how galaxies form is deeply incomplete, or that the broader model governing the evolution of the universe needs to be revised in a more fundamental way. The initial reaction within the scientific community was not to abandon the model, but to search for more conventional explanations. And one of the most promising came from a closer examination of how these galaxies were being observed. It turns out that many of the most extreme objects, sometimes referred to as little red dots, were not as straightforward as they appeared, because at their centers lurked rapidly growing black holes, devouring gas at such intense rates that the infalling material heated up and emitted enormous amounts of radiation from billions of light years away. This radiation blends with the light from stars, making the galaxy appear far brighter, and therefore more massive than it actually is. In effect, the black hole acts like a hidden amplifier, inflating the apparent size of the galaxy without requiring an equally large number of stars. When researchers, including Catherine Swarovski, accounted for this effect and removed these misleading sources from the data, the picture became less extreme, and many of the previously alarming galaxies fell back into a range that the standard model could accommodate for a moment. It seemed as though the crisis might soften, that what looked like a dramatic contradiction could be explained through a better understanding of astrophysical processes rather than a need for new fundamental physics. But the relief was only partial, because even after these corrections, a significant excess of massive galaxies remained, roughly twice as many as the model would predict for that early epoch. This is where the discomfort returns. Quieter than before, but more persistent, because now the discrepancy is no longer dramatic enough to force an immediate overhaul, yet too consistent to be ignored. It suggests that something about the early universe allowed galaxies to form stars more efficiently or more rapidly than they do today, perhaps due to denser environments or different physical conditions that have not been fully captured in existing models. And so, what began as a seemingly impossible observation has transformed into something more subtle and more intriguing. Not a direct contradiction, but a deviation that bends the expectations of cosmology without quite breaking them, leaving you in a position where the universe still makes sense, but not in the way you thought it did. If the story ended with galaxies forming a little faster than expected, you might still be able to convince yourself that this is just a matter of refining astrophysics, adjusting parameters, improving simulations. But what comes next makes that comfort much harder to hold on to, because now it is not just about how many galaxies exist or how massive they are. It is about how they are structured, how they look, how they behave. And those details are beginning to suggest that the early universe was not simply a scaled-down version of what we see today, but something qualitatively different, something that does not quite follow the developmental timeline we thought we understood. One of the most striking examples is the discovery of a massive spiral galaxy, quickly nicknamed the Big Wheel, observed by the James Webb Space Telescope at a time when the universe was still in its relative infancy, less than 2 billion years old. Spiral galaxies are not supposed to appear that early, not in any clean, well-ordered form, because their structure requires time, stability, and a relatively calm environment in which matter can settle into a rotating disk without being constantly disrupted by violent mergers. In the standard picture, the early universe is chaotic, all turbulent, dominated by collisions and irregular growth, a place where galaxies are messy, clumpy, and far from the elegant spirals we associate with maturity. And yet here is a galaxy that seems to have skipped that chaotic adolescence, assembling itself in a way that looks almost too orderly, as if it had found a shortcut through cosmic evolution. At the same time, other observations tell a very different story. Because when astronomers examine large samples of galaxies from that same era, many of them do fit the expected picture of disorder, appearing irregular, fragmented, and dynamically unsettled, which creates a strange coexistence of extremes. A universe where some galaxies are still struggling to take shape while others already resemble the kind of stable systems that should require billions more years to develop. This is not a contradiction in the simple sense, but it is a tension in the narrative of cosmic evolution, because the model does not naturally predict such a wide spread of structural maturity within the same epoch. And then there are the shapes themselves. Because a growing number of early galaxies observed by Webb do not appear as roughly spherical or disk-like systems, but as elongated, stretched forms, almost like cosmic cigars, a morphology that stands out against the expectations of the cold dark matter model, which serves as the backbone of standard cosmology. In that model, dark matter forms clumpy halos that guide the formation of galaxies, leading to structures that tend to be more rounded or irregular rather than strongly elongated. The presence of these prolate shapes suggests that matter may have been flowing along smoother, filament-like structures, which aligns more naturally with alternative models such as warm dark matter or wave dark matter, where the behavior of the underlying particles leads to different large-scale patterns. This is where the implications become much deeper than they might first appear, because dark matter is not just one component among many. It is the scaffolding upon which the entire cosmic structure is built, determining how galaxies form, how they cluster, and how matter is distributed across the universe, if its properties are even slightly different from what we have assumed. If the particles are lighter or behave more like waves than discrete clumps, then the consequences ripple outward into almost every prediction the model makes. From the number of small satellite galaxies orbiting larger ones to the way gravity bends light in gravitational lensing. You are not adjusting a detail at the edge of the theory. You are potentially altering its foundation. And yet, even here, the situation resists a clean conclusion, because none of these observations alone is strong enough to overturn the standard model. And taken together, they do not form a single unified contradiction, but rather a pattern of subtle deviations, each one bending the expectations slightly, collectively suggesting that the early universe may have been more efficient, more structured, and more diverse in its behavior than our current framework comfortably allows. It is as if you are looking at a familiar landscape through a slightly distorted lens, where everything is recognizable, yet just different enough to make you question whether you are seeing the full picture or only an approximation shaped by the limits of your assumptions. At this point, it would be easy to frame everything you have just seen as a failure, to say that something has gone wrong, that the model is breaking, that cosmology has reached a kind of dead end where its most trusted ideas can no longer hold together under the weight of new data. But that interpretation misses something essential, because what you are actually witnessing is not the collapse of understanding. It is the moment where understanding reaches its boundary and begins to push beyond it. The standard model of cosmology is still one of the most successful frameworks ever constructed. It explains the cosmic microwave background with astonishing precision. It predicts the abundance of light elements. It describes how galaxies cluster across billions of light years. And no competing theory comes close to matching its breadth and accuracy. Which means that whatever is happening now is not a replacement of everything we know, but an extension, a refinement, a recognition that the map we have been using is incomplete rather than incorrect. The tensions you have followed, the disagreement in the Hubble constant, the unexpectedly mature galaxies, the strange structures that hint at alternative forms of dark matter, they do not point to chaos. They point to missing pieces, subtle effects that only become visible once measurements reach a certain level of precision. There is even another, quieter discrepancy known as the S8 tension, which concerns how matter is distributed across the universe, how clumpy it is on large scales. And once again, the observations consistently show slightly less clustering than the standard model predicts. Not enough to cause alarm on its own, but enough to echo the same pattern you have already seen. A small but persistent deviation that refuses to disappear. When you step back and look at all of this together, it begins to feel less like a collection of unrelated anomalies and more like a set of clues pointing toward something deeper. Something that lies in the gap between the early universe and the present. In the billions of years of evolution that we cannot observe directly but can only infer through models and indirect evidence. One possibility that has gained attention is the idea of early dark energy, a brief phase in the young universe where an additional form of energy caused space to expand slightly faster than expected before fading away, leaving behind a subtle imprint that shifts the predictions of the model without disrupting its overall success. It is an elegant idea because it does not destroy the existing framework. It modifies it just enough to reconcile the tension, like adding a missing term to an equation that suddenly brings everything into alignment. But whether that idea is correct or not is almost beside the point, because the deeper lesson here is about how science progresses when it encounters contradictions that cannot be ignored. These moments feel uncomfortable, even destabilizing, because they force a confrontation with the limits of current knowledge. Yet historically, they have been the very moments that lead to the most profound breakthroughs. In the 1990s, cosmology faced a different crisis when measurements suggested that the universe might be younger than its oldest stars, a contradiction that seemed impossible until the discovery of dark energy revealed that the expansion of the universe is accelerating, reshaping the entire picture in a way no one had anticipated. What looked like a fatal flaw turned out to be the shadow of something far more fundamental. You are standing in a similar moment now, whether you realize it or not, on a small planet orbiting an ordinary star, using instruments and mathematics to probe a universe that is vast beyond comprehension, and discovering that even with all this knowledge, there are still aspects of reality that slip through the framework we have built. It might seem absurd that a difference of a few percent in a single number could carry such weight, but that is precisely how science works at its most advanced levels, where small discrepancies are often the only visible signs of deeper truths waiting to be uncovered. So this is not the end of the story. It is the beginning of a new chapter, one where the questions become sharper, the models become more flexible, and the picture of the universe becomes even more strange and more beautiful than before. Because every time physics has faced a crisis like this, it has not closed a door, it has opened one. And if you follow that door far enough, you may find that the universe is not just expanding faster than we thought, but that it is revealing a layer of reality that we have only just begun to imagine.